In this question, we have a particle, a neon atom, that is 20U, and it collides onto another particle that's at rest. After the collision, this atom moves in a direction that's 55.6 degrees to the original direction, and the particle originally at rest moves with an angle of 50 degrees. And knowing these 2 degrees, we are asked to find what is the mass of this particle. So let's call this A, call this B. We want to find the mass of B. And there are several ways of doing it. So what we've been doing so far is every time we see questions like those, we always write down the conservation of momentum in the x-axis and the y-axis. And we write down the conservation of kinetic energy. Like this question is also about elastic collision, so we also have the conservation of kinetic energy. But this question, after the question, it says that hint, you could use the law of sines. So I will use a different approach in this question. I will try to use the law of sines just because it suggests that we can do so. And the law of sines might or may not make this question easier. It depends on what you think is easier. But let's just do it as a different approach. So firstly, let's review what the law of sines is in case you have forget a little bit. And so for every triangle, say ABC, let's say we have 3 different angles, alpha, beta, gamma. So the law of sines says that for any 2 different sides, say side BC and side AC, the ratio of their lengths is equal to the ratio of the sine of the angle opposing it. So for BC, it's facing angle alpha. So it's sine alpha. And for AC, it's facing angle beta. So the length of BC over AC is equal to the sine of the angle facing the side. So that is a law of sines. How do we use that to this question? I think what it wants from us is it wants us to use vector addition for the velocity. Because from the conservation of momentum, we have ma va equals ma va prime plus mb bb prime. Previously, what we've been doing is we have always decomposed VA and VA prime and VB prime into 2 directions, into the x direction and the y direction, and then we try to do these 2 directions separately to find those components separately. But if this question wants us to use vector addition, what we will do is we will deal with them as vectors instead of as vector components. So then we'll try to draw this vector addition plots. So MA, we already know, is in this direction, and it's equal to the sum of these. So we are trying to draw these in the addition triangle. MVA prime, we already know it's 50.6 degrees. Let's just call this theta, knowing theta is 50.6 degrees. So this is MAVA, that's the length of it. This is MAVA prime. And this is MB VB prime. And we know this angle, which is also equal to this angle, is 50 degrees. And of course, from those, we can infer that this angle equals 180 minus 50.6 minus 50, which is equal to 74.4 degrees. So using the same law of sine that we've used before, this tells us that MAVA prime, say these 2, over MAVA equals to sine of phi over sine of alpha. So that tells us that VA prime equals VA times sine phi over sine alpha. And similarly, we can do that with, say, these 2 sides. We can have MB VB prime over MAVA prime equals sine theta over sine alpha, and that gives us VP prime equals VA MA over MB on sine theta over sine alpha. So this law of sine pretty much, it gives us an easy way to express the relationship between VA prime and VB prime in terms of as quantities. And now what we can do is we can substitute this relationship into the conservation of kinetic energy. Let's write down the conservation of kinetic energy is 1/2 MAVA squared equals 1/2 of MAVA prime squared plus MBVB prime squared, and 1/2 cancels. So if we just try to plug in these two expressions, what we get is MA VA sine phi over sine alpha squared plus MB VA times MA over MB sine theta over sine alpha squared. So everything in this equation is known except, in this equation everything is known except MB. So we can just rearrange this equation so that we have MB on the left-hand side and everything in the right-hand side. So just with a little bit rearrangement, since I'm running out of space, I just write the results here. I have MB equals MA sine square theta over sine square alpha minus sine square phi. If you do a careful rearrangement of this equation, you should be getting the same expression. And then we plug in all the numbers. It's 20u times sine square 55.6 degree over sine square 74.4 degree minus sine square 50 degree. And that gives us 39.9 u. So that is to say, this second particle, it's actually about twice the mass of the first particle that hits it. And yes, that is the mass of the ball B that we're looking for.